This is Logic and Computer Design Fundamental class, and today we will discuss in Chapter 7, registers. Registers. A register actually is a collection of binary storage elements. You know, when you have a programming language and you define variables as integers or as any representations. Let's say that in C or Java, you define int x. This x must be saved somewhere in the hardware. And this is where we save it, inside a register that is really close to the CPU. In theory, a register is sequential logic, which can be defined by a state table. More often, think of a register as storing a vector of binary values. Meaning, if you define an integer as 8 bits, then it's a collective of 8 storage elements connected together to save the value. Frequently used to perform simple data storage and data movement and processing operations. This is a simple 2-bit register. You can see that we used 2 D flip-flops with the same clock going to both of them. And there are the inputs in the circuit, input 0 and input 1. Those are the values that we want to store inside the flip-flop. And there are the 2 outputs, Y0 and Y1. If you were asked how many states are there, because this is now a sequential circuit, there are 2 to the power of 2. This 2 is representing the number of the flip-flops, which is equal to 4. So you can store the value 0, 0, or 0, 1, or 1, 0, or 1. If you were asked how many input combinations are there, similarly, there are 2 to the power of 2, which is equal to 4. These inputs are residing in the input of the 2 flip-flops. How many outputs combination? Same thing, but now we look at them from the output side. What is the output function? The function y is equal to the value inside the flip-flops, which is a being A0 and A1. What is the next state function? The next state function is dA equal to the input. So dA1 will be equal to input 1, and dA0 will be equal to input 0. You can see that the functions are fairly easy, and you can get them directly from the block diagram of the register. If you were asked, is this a melee or more machine? This is more machine because the outputs is associated with the states. Now, you see the quantities that we see above, most of them are 2 to the power of 2, 2 to the power of 2, and so on. So if you have 2-bit register, then you have 2 to the power of 2. If you have n-bit register, then it's going to be 2 to the power of n. 2 bits, you have 2 flip-flops. If there are n bits, then you have n different flip-flops. Now, this is the state tables. We don't really need it, but because this is a simple register, it's just saving the value of coming from the input inside the flip-flop. However, if you want to develop the state table, you can see that the current state being 0, 0, 1, 0, 0, 1, or 1, 1. Now, the next states, based on the input 0 and input 1. If the input is 0, 0, then you will store the input inside the flip-flop. If the input is 1, 0, then you will store the value. Similarly for 0, 1, and 1, 1. Now for the output is associated with the current state, as you can see here. Now, the previous register was the simplest form of register. Here we have a 2-bit register with load control. So you can see that we can develop registers with load controlled feedback. Meaning, before each flip-flop, the flip-flop, we have a multiplexer that chooses between 2 inputs. The first one is inputs, the main input. For example, here it's input 1. And the second one is a feedback from the output of the flip-flop. So if the load is equal to 0, meaning that we don't want to load an input from outside, we want to keep the same value. So we load the register contents by having the feedback. So you hold the current values. If the load is equal to 1, the meaning that we want to load the input, the outside input inside the flip-flop. So you load this input value, which will be new values. This is for this flip-flop and also for this flip-flop. And no matter how many bit registers you have, you will have n different flip-flops. You can see that those 2 flip-flops, it's kind of separated from each other. The only common value, or the only 2 common values between them, are the clock and the load control. Now, the idea that after we define this simple register, we will move to shift registers. A shift register is also a sequential logic block made up of flip-flops that allows parallel or serial loading and serial or parallel outputs, as well as shifting bit by bit. An example of a shift register at work would be the calculator that everybody knows. If you can see, if you press 3, it shows up in the screen. If you press 6, there will be a shift and a loading of the value 6. If you press 8 after this, then there will be a shift and you insert the 8, and then at the end you have a shift and you insert the new value 4. So you can see that the application of shift registers have a lot of different benefits, and the calculator is one of the famous examples. Now, we said that the inputs and the outputs of a shift register could be parallel or serial. So as you can see here, we have a serial input and a serial output of different blocks. Those blocks, each one of them would be a D flip-flop. And you shift the values that comes here bit by bit inside this the pipe of blocks, and then at the same time you are shifting a new value in, you will shift a value out. This type is called SISO, which means serial input and serial output. Notice here that all the serial inputs will be entered in the most significant bit position, and the output will be the exit of the bits from the least significant bit position. Now, there are other types. Actually, there are 4 types, and this is the first one, the SISO. The second one is if you have a serial in, but the output now are parallel, meaning you output all the bits in one clock cycle at the same time. You output all of them together. While serially, you enter, or for the previous example, either when you're talking serial in the input or the output, you get them bit by bit. So in one clock, you will get a bit over here, and you will get a bit output from here. The next clock, the next bit will get in, and the next bit will also get out. This is the serial type SISO. Now, if you have a parallel output, the output is getting out at the same times for all the bits. Now, this type is actually called SIPO, serial and parallel out. Next type, this is the second type. Now, the third type is PIPO, which will be parallel in, parallel out. This is the fastest type where you can load the bits inside the register and save them for some time if you want. And then if you want to get them out, you get them parallel in a parallel way at the same clock cycle. Now, the last type, the fourth type, is PISO, which is parallel in. You get the inputs in parallel form. In one cycle, you get all of the input in. And if you want to get the output, you only get them bit by bit serial. To see one of the types in motion, this is the shift register, shifting the data bit by bit inside the shift register. And when the other data clock happens or get inside the latch, the value gets to the output. You can see that now we put the input serially, bit by bit inside. And when the signal happens, you in a parallel way, you get the output and save them inside the storage element. Of course, this is a sequential circuit, and it's dominated by the clock cycle. This second data here is like a latching bit when it is 1, you save whatever value you have in the shift register inside the storage register, and you show it in the output on the LEDs. As you can see, whenever there is a 0, it will be off, 1, it will be on. Now, the shift registers move the data laterally within the register towards its most significant bit or least significant bit position based on where is the input and where is the output. Now, here, if we have a clock, the clock would be common in all the D flip-flops. And now we have the input here. It will go inside the first D flip-flop. The output of the first D flip-flop would be the input of the second D flip-flop, and so on. In the simplest case, the shift register is simply a set of D flip-flops connected in a row, like what you see here. The data inputs in is called a serial input. This is a serial input, and it's going to be shifted to the right direction. The data output, the out, is often called a serial, also a serial out. So this is SISO, serial input and serial output. Now the vector A, B, C, and output is called the parallel output if you want to get them together. If you want to get this A, B, and C, and the output together at the same clock cycle, then they are going to be parallel. Now, to see the operation of the shift register, now we have the clock entered to, or the clock cycle was going to be an input to all of the clock, to all of the flip-flops, which means that whenever there is a rising, this is a rising edge flip-flop, whenever there is a rising, this rising will happen at the same time for all the flip-flops. Now, if we have those cycles beginning from T0, T1, T2, T3, 4, 5, and 6, meaning that at this time we have the first rising, at this time we have the second rising, and so on. This is what's going to happen inside the shift register. At the beginning, we want that to have the input serially as 0, 1, 1, 0, 1, 1, and 1, which means that the input would be like this: 0, 1, 1, 0, 1, 1, 1. And they will be shifted in this direction to the right. So first you will get 0 in the first cycle. The next cycle you will get 1. The next cycle you will get 1, and so on. So this 0 will be in the first cycle. This is in the second cycle, and so on. This is cycle 0, cycle 1, cycle 2, cycle 3, cycle 4, and so on. Now, what happens in the shifting, at the beginning, when you have only 0, we don't really know what's inside the flip-flops in A, B, and C, and also the output. We have no idea. Now, in the next cycle, the 0 that was here, it will be shifted over here, indicated by this arrow. So the 0 that was that was an input in the first, or in clock cycle 0, it would be inside the flip-flop of A in the next cycle, which is cycle 1. And you can see after, if we have these inputs here, after 4 cycles, cycle 0, 1, 2, 3, and then in the 4th cycle, the first input 0 would be showed in the output, and then followed by 1, followed by 1, followed by 0, and then the new input would be 1. So you can see right now at T4, if this is the current clock cycle, we have 4 bits already inserted inside the shift register. So there will be 0, 1, and 1, and 0 stored inside the flip-flop, and there will be a new input waiting to be shifted inside the first flip-flop. After this, shifting this one inside will drop this 1, 0, will drop this 0 value to the output, meaning that it's going to be pushed outside. This is why it's going to be dropped. It's not showing anymore in the table, this 0, and this one would be replacing it. In the next cycle, this will be taking out, and the new one will be shifted. You can see the diagonal behavior of the inputs. The first one 0, and then it will be shifted each cycle to the next position. The next input shifted this way, and so on to the last bit. Now, here in this table, any initial unknown states are denoted by a question mark. Sometimes we denote them by don't care. So basically, T0 is the register state just before the first clock pulse occur. T1 is after the first pulse and before the second pulse. Now, we also can have parallel load shift register. They are not normal registers, they are shift register. So there is a shifting behavior with the capability of loading a new input. To do this, we need to add muxes between each shift register stage. So before there was this flip-flop and this flip-flop close to each other, only a line between. Now, instead of a line, we have 2-to-1 multiplexer here. And similarly, we have 2-to-1 multiplexer here. Your control is called shift. If the shift is equal to 1, this means that this input would be 1. And it would have the input going inside the first flip-flop and then going outside and then getting in the second flip-flop. And this is the shifting behavior, the one that we had here. This one goes here and then goes to the next one. This is if the shift is high or equal to 1. And this is what we said here. If the shift is high, the data shifts to the right, meaning the right direction, on each clock cycle. Now, if the shift is low or 0, this means now this would be 0, and now this one is going to be active. So the input DA will be inserted inside this flip-flop, and at the same clock cycle, DB will be inserted and saved inside this flip-flop. Now, if you add more bits, we can make an n-bit parallel load shift register. This one is only 2 bits. The same idea in all of the types that we studied so far is the clock cycle is going to be inserted in both of the flip-flops here, meaning that at the rising edge, this flip-flop will pass the value inside, and this one will pass its value and store it inside. Now, there are shift register with additional functions. We discussed some of them, like the loading and shifting to the right. Now, by placing a 4-input multiplexer in front of each D flip-flop, instead of the 2-to-1 multiplexer, we have 4-to-1. We can implement a circuit with many functionality. Some of them, probably, we shift to the right, shift to the left, and we have parallel load, or we hold the value, no shifting to the right or the left, and no also loading, you just hold the data. So this is for different functionality, and you can do them by having a larger multiplexer. Now, the shift register can also be designed to have different functionality. For example, shifting more than a single bit position to the right. So instead of shifting by 1 bit, you shift by 2 or 3 bits. Similarly, you do this for the left. The shift register can be designed to shift a variable number of bits, position specified by a variable, and this variable could be called a shift amount. A shift amount. Now, the register file is a collective group of different or similar registers. A register is an array of D flip-flop, as we said before. A register file is a state element that consists of a set of registers that can be read and written by supplying a register number to be accessed, meaning that you need to know which register you want to access, so you have to have its address. If you have n registers, this is going to be register 0, register 1, and so on, up to register n-1. Now, each one of these registers is an n-bit, or let's say m-bit register, meaning it has m flip-flops. For example, if we say that register 0 has 8 is an 8-bit register, meaning inside it there will be 8 flip-flops. If we say that we have 32 different registers, meaning that now n is equal to 32. The first one is 0, 1, up to 31. So we have 31 different registers. Each one of them have 8 bits. Now, this block is called a register file. And in the register file, one of the jobs that the register file do, if you have an operation like this, if you want C is equal to A plus B, and this is, for example, an let's say B, and for example, this is an operation in a C language. So this is one statement on the C, and you want to execute it. What happened in the register file, if you want, the register file will have all the variables, A, B, C, and other variables. So you need to access A and B, and you need to read them or load them. So you load them first, do the operation, and then you store the value inside the C. In another way, we say that we need to read A and B, do the operation, and then write the result into C. So the keywords here, read or load, it's the same meaning here. The other keyword is write or store. So right now we need to read 2 different variables. To read A and B from the register value, we need to tell the register value where are they. So we give them the read register number 1. So let's say that A was stored in register. Let's say that A was here in register 0 and B was here in register 1. So we have to give them here the number 0 and here the number 1, meaning that we want register 0 and register 2 values. Now the register file understand this by doing what you see in this block. It tells, okay, I need 0 and 1 here, meaning that this is going to be the selector and this mux. I will get 0 by having the A to the getting the A to the output. Now you will have the value of A going outside into read data 1. So you'll have A here. Similarly for the B, now the B will be here, so you will get it outside because you have 1 in the control of the mux or in the selector of the mux, and you get it outside, so you'll have B over here. Now after this, another block, do the computation, finish the computation, and then it wants to store the result of the addition of A plus B. Let's say A is 5 and B is 7. So the addition of them are 12. So the 12, the result 12 should be saved inside the register file. So there will be another block. Usually this is the ALU. Will do the computation and give you the result here in the right data, which is going to be 12. And you need to know where do you want to store the 12. If we say that we want to store the 12 in register number 30, let's say. So what happens here, you will give the register number 30 right here, and you will give the data 12 here. So to save the value inside the correct register, we said that the registers start from 0, 1, and we will assume that we have 32 registers. So this is going to be 31, and this is going to be 30, or register number 30. So what happens? You will have n to 2 to the power of n decoder which will be the 2 to the power of n would be 32, because there will be 32 different lines going out from the decoder and going to each of the registers. And notice that it doesn't go directly, it's AND gated with a control called the write. If you want to write, the write should be 1. If you don't want to write, which is this one here, right? If you don't want to write, it would be 0. This is for protecting the register. To protect the registers, you only write when the signals is equal to 1. So right now we want to write, so we will make this 1. The register number is going to be a binary value representing the value 30. So it's going to be 5 bits. 5 bits. So you will have 30. 30 would be 0, 1, 1, 1, and 1. This is the value 30. 5 bits. This will activate this line. And this one is going to be 1 because the write is 1. The other will be 0. There is no connections in all of the other ANDs. Only this one will put the result inside. So it will activate the clock of this register, meaning it will give it a rising. And because of the rising going to all the different flip-flops, the value 12 will be inserted and saved inside this 8-bit registers. And this is called a register file. Some register files have write control only. Some of them have write and they also have read control.